In 1783, a massive fissure opened in Iceland's Lakey region, releasing toxic gases that killed one-fifth of the island's population. But the catastrophe didn't stop there. The volcanic eruption altered weather patterns across the entire northern hemisphere, triggering crop failures from Japan to North America. Scientists analyzing ice cores from this event discovered something that should be impossible: chemical signatures in the atmospheric fallout that don't match any known volcanic process. Today, we examine 101 facts about our planet that challenge everything we thought we understood about the world beneath our feet. Prepare yourselves, we begin. Earth spins at 1,000 miles per hour at the equator, yet we feel nothing. This rotation creates a bulge that makes our planet 27 miles wider at the equator than between the poles. The centrifugal force is so powerful that if Earth stopped spinning suddenly, everything not anchored to bedrock would continue moving eastward at supersonic speeds, creating worldwide destruction that would make any asteroid impact seem trivial by comparison. But here's what scientists rarely discuss. Earth's rotation is slowing down. Every century, our day lengthens by approximately 1.7 milliseconds. This deceleration has been measured precisely through atomic clocks and astronomical observations dating back thousands of years. Ancient eclipse records from Babylonian astronomers show that days were measurably shorter in the past, and the trend continues today. The implications are staggering. 4 billion years ago, when Earth first formed, a day lasted only 4 hours. The planet spun so rapidly that hurricane-force winds circled the globe perpetually, and any standing water would have been flung toward the equator by centrifugal force. This rapid rotation rate suggests that early Earth was a radically different world than what we see today, with atmospheric and oceanic circulation patterns that have no modern equivalent. But what's causing the slowdown? Traditional explanations point to tidal friction with the moon. As ocean tides slosh across Earth's surface, they create drag that gradually transfers rotational energy to the moon's orbit, simultaneously slowing Earth's spin and pushing the moon farther away. This process is well documented and continues at a rate of 3.8 centimeters per year for lunar orbital distance. However, recent measurements reveal anomalies in the deceleration rate that don't match tidal friction models. Earth appears to be slowing down faster than it should be, suggesting that additional forces are at work. Some geophysicists have detected variations in the planet's moment of inertia that correlate with deep mantle convection patterns, indicating that internal geological processes may be affecting rotation in ways we don't fully understand. The planet's magnetic field reverses completely every 200,000 to 300,000 years on average, though the timing is highly irregular. During these reversals, the magnetic field doesn't simply flip overnight. Instead, it weakens dramatically over a period of thousands of years, sometimes developing multiple magnetic poles scattered across the globe before eventually settling into a new, reversed configuration. We are currently experiencing one of these weakening phases. Earth's magnetic field has decreased in strength by approximately 9% over the past 180 years, with the rate of decline accelerating in recent decades. The South Atlantic anomaly, a region of particularly weak magnetic field strength, stretching from South America to Southern Africa, has grown significantly larger and continues to expand. But here's where the mystery deepens. Geological evidence preserved in volcanic rocks reveals that some past magnetic reversals occurred with remarkable speed. Lava flows in Oregon show evidence of a magnetic field shift of 53 degrees in a single year, recorded approximately 15 million years ago. This rate of change is thousands of times faster than current models predict should be possible. The rapid reversal evidence challenges fundamental assumptions about how Earth's magnetic field operates. The field is generated by convection currents in the liquid iron outer core, a process that should involve timescales of centuries or millennia due to the enormous thermal inertia of molten metal. Yet the geological record clearly shows that the field can reorganize itself with startling rapidity under certain conditions. Ocean depths remain more thoroughly unmapped than the surface of Mars or the Moon. We have detailed topographic data for only 20% of the seafloor at the resolution necessary to identify features smaller than 5 kilometers across. The remaining 80% of Earth's ocean floor is known only through satellite gravity measurements that can detect large underwater mountains and trenches, but miss smaller features entirely. This lack of knowledge has profound implications. Thousands of undersea volcanic vents remain undiscovered, each potentially hosting unique ecosystems and mineral deposits. Deep ocean trenches contain environments where pressures exceed 1,000 atmospheres, creating conditions so extreme that water behaves differently than at the surface. At these pressures, water molecules pack more tightly together, increasing density and altering chemical properties in ways that remain poorly understood. Recent deep-sea missions have discovered underwater lakes and rivers on the ocean floor. These brine pools form when salt deposits dissolve and create pockets of extremely salty water that is denser than surrounding seawater. The brine pools don't mix with the ocean above them, but instead form distinct bodies of water with their own currents, waves, and shorelines, all existing underwater at depths where sunlight never penetrates. These submarine lakes host bizarre ecosystems of bacteria and organisms adapted to extreme salinity and pressure. Some of these underwater pools contain methane concentrations so high that they would be toxic to surface life. Yet specialized microbes thrive in the environment, metabolizing chemicals that would kill conventional organisms instantly. The discovery of underwater brine pools forces reconsideration of what defines a lake or ocean. We have lakes within oceans, each with distinct chemistry and biology, challenging the simple categorization systems we use to understand planetary hydrology. But the deep ocean holds even stranger secrets. In 1997, hydrophones detected an ultra-low frequency sound so powerful that it was recorded by sensors over 5,000 kilometers apart. Named the bloop, this sound matched the profile of a living creature, but would have to be several times larger than a blue whale to produce such volume. The sound has never been definitively explained, though some scientists attribute it to ice calving events in Antarctica. Yet the acoustic signature doesn't perfectly match known ice-related sounds. And the source location in the remote Pacific Ocean raises questions about what could generate such powerful acoustic emissions in one of Earth's most isolated regions. Earth's atmosphere extends far beyond what most people imagine. The exosphere, the outermost layer of our atmosphere, reaches halfway to the moon. At these extreme altitudes, atmospheric density drops to near vacuum, but individual atoms of hydrogen and helium still orbit Earth in trajectories that blur the distinction between atmosphere and space. The Kármán line, at 100 kilometers altitude, represents the commonly accepted boundary of space, but this definition is arbitrary. Atmospheric drag affects satellites at altitudes above 500 kilometers, and the International Space Station requires periodic reboost maneuvers to compensate for atmospheric friction, despite orbiting at 400 kilometers above Earth's surface. Auroras have been detected at altitudes exceeding 1,000 kilometers, nearly 3 times higher than the International Space Station orbits. These extreme altitude auroras involve different physical processes than the familiar green and red curtains visible from Earth's surface. At such heights, individual oxygen atoms, excited by solar wind particles, emit ultraviolet light invisible to human eyes, but detectable by specialized instruments. The existence of these high-altitude auroras reveals that solar wind penetrates deeper into Earth's magnetic field than previously believed. During severe geomagnetic storms, particles from the sun can reach altitudes where they interact with satellite electronics and navigation systems, creating technological hazards that ground-based auroras never produce. Lightning strikes Earth approximately 100 times every second, totaling nearly 8.6 million strikes per day. The majority of these strikes occur over tropical landmasses, where atmospheric convection is strongest. Lake Maracaibo in Venezuela experiences more lightning than any other location on Earth, with thunderstorms occurring approximately 260 nights per year due to unique geographical and meteorological conditions. Individual lightning bolts carry currents exceeding 30,000 amperes and reach temperatures of 30,000 degrees Celsius, 5 times hotter than the surface of the sun. The extreme temperature causes explosive expansion of air that creates thunder, with sound waves powerful enough to shatter windows near direct strike locations. But lightning's effects extend far beyond simple electrical discharge. Each lightning strike produces a burst of gamma rays, making thunderstorms the most powerful natural particle accelerators on Earth. These terrestrial gamma ray flashes were discovered accidentally by satellites designed to detect gamma rays from distant cosmic sources. The gamma ray emissions from lightning exceed the energy output of many astronomical phenomena and can be detected from space. The mechanism behind gamma ray production in thunderstorms involves runaway electron avalanches, where cosmic rays trigger cascades of electrons that accelerate to relativistic speeds in Earth's electric field. These electron beams produce gamma rays through Bremsstrahlung radiation when they collide with air molecules. The discovery that ordinary thunderstorms produce gamma rays challenges assumptions about atmospheric electricity and reveals that processes once thought to occur only in space. Physics laboratories happen routinely in Earth's atmosphere during every major storm system. Lightning also produces antimatter. During thunderstorms, high-energy gamma rays interact with air molecules to create electron-positron pairs through a process called pair production. The positrons, antimatter equivalents of electrons, exist for only milliseconds before annihilating with electrons and producing characteristic gamma ray emissions. This means that Earth's atmosphere regularly produces and destroys antimatter, making our planet a natural antimatter factory, operating continuously during thunderstorm activity. Earth contains more trees than stars in the Milky Way galaxy. Recent estimates using satellite imagery and ground surveys suggest that approximately 3 trillion trees exist on Earth, compared to 100 to 400 billion stars in our galaxy. This number is simultaneously impressive and troubling. Before human civilization began large-scale deforestation, Earth likely contained approximately 6 trillion trees, meaning we have reduced global tree populations by roughly 50% through agricultural expansion and urban development. The current rate of deforestation eliminates approximately 15 billion trees annually, though reforestation efforts replace about 5 billion trees per year, creating a net loss of 10 billion trees annually. At this rate, Earth loses the equivalent of a forest the size of Panama every year. Individual trees can be far older than most people imagine. Bristlecone pines in California's White Mountains include specimens over 5,000 years old, making them among the oldest known individual organisms on Earth. These ancient trees were already mature when the pyramids were built and have survived millennia of climate variation, fires, and storms through adaptation strategies that slow their metabolism to barely measurable levels. But the oldest individual trees are dwarfed by clonal organisms. A quaking aspen colony in Utah named Pando consists of over 47,000 individual tree stems that share a single root system. This colony weighs approximately 6,000 metric tons and may be 80,000 years old, based on growth rate estimates, making it one of Earth's oldest and heaviest organisms. The ocean contains approximately 20 million tons of gold in dissolved form. This enormous quantity sounds like it should be economically significant, but the gold is dispersed at concentrations of approximately 13 billionths of a gram per liter of seawater. Extracting gold from seawater would require processing impossibly vast volumes of water and would consume far more energy than the recovered gold would be worth. Nevertheless, the total quantity of dissolved gold in Earth's oceans exceeds all the gold ever mined by humanity by several orders of magnitude. The gold exists in ionic form, dissolved from rocks and minerals through billions of years of weathering and erosion. Rivers continuously transport microscopic quantities of gold into the ocean, while biological and chemical processes occasionally remove gold from seawater through precipitation and incorporation into marine sediments. Ocean water also contains virtually every other element on the periodic table in trace quantities. Uranium, silver, copper, and rare earth elements all exist in dissolved form, creating a vast dilute repository of minerals that future technologies might learn to extract efficiently. But the ocean's most valuable resource isn't its dissolved minerals, but its capacity for heat storage. Ocean water has enormous heat capacity compared to air, meaning the top few meters of ocean water contain more thermal energy than the entire atmosphere. Now, this heat storage moderates global climate and drives weather patterns through energy exchange between ocean and atmosphere. Earth's oceans contain 97% of all water on the planet. Of the remaining 3% that exists as freshwater, approximately 2/3 is locked in glaciers and ice caps, leaving less than 1% of Earth's total water readily accessible as liquid freshwater in lakes, rivers, and groundwater. This means that 0.3% of Earth's water supplies all terrestrial ecosystems and human civilization. The distribution of this freshwater is extremely uneven. Lake Baikal in Siberia contains approximately 20% of the world's unfrozen freshwater, despite being a single lake. The lake reaches depths of 1,642 meters and contains more water than all of North America's Great Lakes combined. Lake Baikal also represents one of Earth's oldest lakes, and having formed approximately 25 million years ago in a continental rift zone that continues to widen today. The lake's extreme age has allowed evolution of unique species found nowhere else on Earth, including the world's only exclusively freshwater seal species. The lake's depth and isolation create environmental conditions so stable that some organisms living in Lake Baikal's depths have remained essentially unchanged for millions of years. These living fossils provide windows into ancient ecosystems and evolutionary processes that have vanished elsewhere on Earth. Earth's deepest point is the Challenger Deep in the Mariana Trench, reaching approximately 10,994 meters below sea level. The pressure at this depth exceeds 1,000 atmospheres, equivalent to having 50 jumbo jets stacked on top of a person. Despite these extreme conditions, high life thrives even in the deepest trenches. Specialized fish, amphipods, and microbes have adapted to conditions that would instantly kill surface organisms. These deep-sea creatures possess proteins and cellular membranes, modified to function under extreme pressure, and some species show genetic adaptations found nowhere else in the biosphere. But here's what makes the deep ocean truly extraordinary. More people have walked on the moon than have visited the bottom of the Mariana Trench. Only 4 descents to Challenger Deep have been completed in human history, compared to 12 astronauts who have walked on the lunar surface. This reveals a profound truth about human exploration priorities. We have invested vastly more resources in exploring space 384,000 kilometers away than in understanding the ocean depths just 11 kilometers below the surface of our own planet. The reason for this disparity lies in engineering challenges. Building spacecraft that can withstand the vacuum of space is actually easier than constructing submersibles that can survive the crushing pressures of the deep ocean. Water pressure increases linearly with depth, meaning that at 11 kilometers down, every square centimeter of surface area experiences over 1,000 kilograms of force. Creating viewing ports and electronic systems that function under such stress requires exotic materials and engineering approaches that exceed the challenges of space travel. Earth's atmosphere weighs approximately 5.5 quadrillion metric tons. This enormous mass of air presses down on Earth's surface with a force of approximately 10 tons per square meter at sea level. We don't feel this pressure because it acts equally in all directions, and our bodies have evolved internal pressures that balance external atmospheric force. The weight of the atmosphere varies with weather conditions. High-pressure systems involve denser air masses that increase surface pressure, while low-pressure systems involve rising air that reduces pressure at ground level. Barometric pressure changes associated with weather systems can vary by 5% or more, representing movements of billions of tons of air across continents. Atmospheric mass distribution affects Earth's rotation rate through conservation of angular momentum. When atmospheric mass shifts toward or away from Earth's equator, the planet's rotation rate changes measurably, creating variations in day length of up to 1 millisecond. These atmospheric effects on rotation are large enough to require corrections in precision timekeeping systems used for GPS navigation and astronomical observations. The atmosphere extends to such altitudes that it captures satellites and space debris through drag forces. Even at 800 kilometers altitude, residual atmospheric particles create enough friction to gradually slow orbiting objects, causing them to spiral downward over months or years until they burn up during re-entry. The highest atmospheric layer, the exosphere, contains such low densities that particles can travel hundreds of kilometers without colliding with other molecules. At these altitudes, the distinction between atmosphere and space becomes arbitrary. They and individual atoms follow ballistic trajectories that can reach altitudes where solar radiation strips electrons away, creating ionized particles that populate Earth's magnetosphere. Some of these ionized particles escape Earth's gravity entirely, stripped away by solar wind and lost to space forever. Earth loses approximately 90 tons of atmosphere to space every day through this process, though the loss rate is trivial compared to the atmosphere's total mass and is balanced by volcanic outgassing and comet impacts that add new atmospheric gases. Earth's core is as hot as the surface of the Sun, reaching temperatures of approximately 5,400 degrees Celsius at the boundary between the solid inner core and liquid outer core. This extreme temperature exists just 6,400 kilometers beneath our feet. Yet, we can never visit it. The deepest hole ever drilled, Russia's Kola super-deep borehole, reached only 12.2 kilometers deep before extreme temperatures and pressure made further drilling impossible. This means humanity has penetrated less than 0.2% of the distance to Earth's core, and we have no realistic technology for drilling deeper. Everything we know about Earth's deep interior comes from indirect observations. Seismic waves from earthquakes, measurements of Earth's gravitational and magnetic fields, and laboratory experiments that recreate deep Earth conditions. These indirect measurements reveal a planetary structure far more complex than simple textbook diagrams suggest. Earth's mantle isn't uniformly mixed, but contains distinct layers with different chemical compositions and physical properties. Subducted oceanic plates descend into the mantle, where they accumulate at the boundary between upper and lower mantle, before eventually sinking deeper or being recycled through mantle convection. The core mantle boundary features dramatic variations in properties that suggest partial melting and chemical reactions between core and mantle materials. Some regions show evidence of ultra-low velocity zones where seismic waves slow dramatically, indicating the presence of partially molten material or exotic phases of minerals that exist nowhere else in Earth's interior. Recent seismic studies have detected what appears to be a distinct innermost inner core, a region at Earth's center where iron crystals orient differently than in the surrounding inner core. So this discovery suggests that Earth's core has even more structural complexity than previously believed, with the innermost region potentially representing the remnant of Earth's original core from planetary formation 4.5 billion years ago. The inner core rotates slightly faster than the rest of the planet, completing an extra rotation relative to Earth's surface approximately every 400 years. This super-rotation results from electromagnetic coupling between the solid inner core and the convecting liquid outer core, though the exact mechanisms remain debated among geophysicists. Earth's magnetic field is generated by convection currents in the liquid outer core, but the field's structure is far from simple. The magnetic poles don't align with the geographic poles, and their positions wander continuously. The North Magnetic Pole has moved over 2,300 kilometers during the past century, accelerating from approximately 15 kilometers per year in 2000 to nearly 55 kilometers per year in recent measurements. This rapid movement suggests changes in core convection patterns that we don't fully understand. The magnetic field also features local anomalies, where field strength varies dramatically over short distances. The South Atlantic anomaly allows charged particles from space to penetrate deeper into the atmosphere than elsewhere, creating increased radiation exposure for satellites and aircraft passing through the region. The anomaly appears to be growing and possibly splitting into two separate regions, suggesting that the weakening magnetic field may be developing multiple poles as a precursor to a complete reversal. But here's what concerns scientists most. During magnetic field reversals, the field doesn't simply switch polarity instantaneously. Instead, it weakens dramatically for thousands of years, while the poles migrate unpredictably, before eventually settling into a new configuration. During these transition periods, Earth's surface receives increased exposure to cosmic radiation and solar wind particles that the magnetic field normally deflects. Geological evidence from past reversals shows no correlation with mass extinction events, suggesting that life survives field reversals without catastrophic consequences. However, modern technological civilization depends heavily on satellites, power grids, and electronic systems that could be disrupted by the increased radiation exposure and geomagnetic storms that occur during field reversals. A reversal occurring today would create challenges that ancient organisms never faced. Continents drift across Earth's surface at rates of approximately 2 to 15 centimeters per year, roughly the same speed at which fingernails grow. This slow movement has dramatic consequences over millions of years. The Atlantic Ocean widens by several centimeters annually as the Americas separate from Europe and Africa, while the Pacific Ocean shrinks as subduction zones around its margins consume oceanic crust faster than new crust forms at mid-ocean ridges. In 250 million years, all continents will likely merge into a new supercontinent, temporarily halting the cycle before the supercontinent breaks apart and the cycle begins again. Earth has experienced at least 3 previous supercontinents: Pangaea 300 million years ago, Rodinia 1 billion years ago, and Columbia 1.8 billion years ago. These supercontinent cycles profoundly affect climate, ocean circulation, and biological evolution. When continents cluster together, interior regions become isolated from oceanic moisture sources, creating vast deserts. Ocean circulation patterns change dramatically, affecting global heat distribution and potentially triggering ice ages or hothouse conditions. Continental collisions build mountain ranges that alter atmospheric circulation and increase weathering rates, drawing carbon dioxide from the atmosphere and potentially cooling global climate. The Himalayas continue to rise today as India collides with Asia at approximately 5 centimeters per year. The collision has already created the world's highest mountain range and continues to drive Tibet upward, creating a plateau averaging over 4,000 meters in elevation across an area larger than Western Europe. But mountain building represents only one consequence of plate tectonics: subduction zones, where oceanic plates descend into the mantle, generate Earth's most powerful earthquakes and explosive volcanic eruptions. The 2011 Tohoku earthquake off Japan's coast released energy equivalent to approximately 600 million times the Hiroshima atomic bomb and shifted Earth's axis by approximately 10 centimeters, changing the length of a day by 1.8 microseconds. Individual earthquakes can reshape entire coastlines. The 1960 Chile earthquake, the most powerful ever recorded at magnitude 9.5, lifted some coastal regions by several meters while dropping others below sea level, so permanently altering the geography of hundreds of kilometers of coastline. Earthquakes in subduction zones can occur at depths exceeding 700 kilometers, far deeper than earthquakes at other plate boundaries. These deep earthquakes involve mechanisms different from shallow quakes, possibly including mineral phase transitions that cause sudden volume changes in descending plates. The deepest earthquakes occur under conditions where rocks should flow plastically rather than fracturing, making their existence a puzzle that geophysicists are still working to solve. Earth contains approximately 1,500 active volcanoes, defined as having erupted within the past 10,000 years. However, this number includes only subaerial volcanoes. The ocean floor hosts countless additional volcanoes, with mid-ocean ridges alone featuring continuous volcanic activity along 65,000 kilometers of underwater mountain ranges. Submarine volcanoes erupt constantly, creating new oceanic crust and driving seafloor spreading. Yet these eruptions occur unseen beneath kilometers of water. Most submarine eruptions are never detected unless they occur in shallow water or produce distinctive seismic signatures. The most volcanically active body in the solar system isn't Earth, but Jupiter's moon, Io. Yet Earth still features remarkable volcanic diversity. Volcanoes range from gently sloping shield volcanoes like those in Hawaii, which erupt relatively fluid basaltic lava, to steep stratovolcanoes like Mount Fuji, which explosively erupt viscous andesitic or rhyolitic magma. Supervolcanoes represent the most dangerous volcanic systems. These enormous calderas can erupt thousands of cubic kilometers of material in single events, causing global climate disruption that lasts years or decades. Yellowstone's caldera has erupted 3 times in the past 2.1 million years, with the most recent eruption occurring 640,000 years ago and ejecting approximately 1,000 cubic kilometers of material. The Toba supervolcano in Indonesia erupted 74,000 years ago, producing the largest volcanic eruption in the past 2 million years. The eruption ejected approximately 2,800 cubic kilometers of material and may have triggered a volcanic winter that lasted a decade, cooling global temperatures by several degrees Celsius. Some researchers have proposed that the Toba eruption created a population bottleneck in human evolution, reducing global human population to perhaps 10,000 individuals. Though this hypothesis remains controversial, regardless of its effect on human populations, the Toba eruption demonstrates that individual volcanic events can affect global climate with severity comparable to asteroid impacts. Earth's largest volcanic features are flood basalt provinces, enormous regions where vast quantities of basaltic lava erupted from fissures and spread across hundreds of thousands of square kilometers. The Siberian Traps flood basalts erupted approximately 252 million years ago, coinciding with the Permian-Triassic mass extinction that eliminated over 90% of marine species. The volume of lava erupted was so enormous that it covered an area larger than Western Europe, with layers of basalt averaging over 1,000 meters thick. The gases released during this eruption would have dramatically altered atmospheric chemistry, potentially creating the environmental stress that drove the mass extinction. Volcanic eruptions have shaped human history in ways that extend far beyond local destruction. The 1815 eruption of Mount Tambora in Indonesia killed approximately 71,000 people directly, but triggered global climate effects that caused widespread crop failures and famine. The year 1816 became known as the Year Without a Summer, as volcanic aerosols in the stratosphere reflected sunlight and cooled temperatures worldwide. Frost and snow occurred in July and August across New England and Europe, destroying crops and causing widespread starvation that killed far more people than the eruption itself. The Earth experiences approximately 500,000 detectable earthquakes every year, though only about 100 of these are strong enough to cause damage, and only 10 to 20 reach magnitudes that can cause significant destruction across large areas. The vast majority of earthquakes are too weak to be felt without seismometers, representing constant microseismic activity as tectonic plates continuously adjust their positions. Earthquake energy increases logarithmically with magnitude. A magnitude 7 earthquake releases approximately 32 times more energy than a magnitude 6, and a magnitude 8 releases 1,000 times more energy than a magnitude 6. This scaling means that the most powerful earthquakes release truly staggering amounts of energy. The 2004 Indian Ocean earthquake that triggered the devastating tsunami released energy equivalent to approximately 23,000 Hiroshima atomic bombs and was so powerful that it made the entire planet vibrate. Seismometers detected these planetary oscillations, which caused Earth to ring like a bell with a period of approximately 54 minutes. The earthquake also caused the planet to wobble slightly on its axis and shortened the length of a day by 6.8 microseconds through redistribution of Earth's mass. The energy released by this single earthquake exceeded the total energy consumption of the United States for 6 months. Earthquakes can trigger other earthquakes thousands of kilometers away through a process called dynamic triggering. Seismic waves from large earthquakes can shake distant faults that are already close to failure, causing them to rupture days or weeks after the initial event. This phenomenon creates earthquake clustering in time, even when the earthquakes occur in widely separated locations. Some earthquake sequences involve swarms of hundreds or thousands of small earthquakes occurring in compact time periods, sometimes without a clear main shock. These swarms can continue for months and appear to involve fluid migration through rock fractures rather than simple fault slip, though the exact mechanisms remain poorly understood. Earth's biosphere extends from approximately 11 kilometers below sea level to at least 10 kilometers above it, though microbes have been found at even greater altitudes and depths. This 20-plus kilometer layer represents the zone where life exists in significant quantities, though the vast majority of biomass concentrates near Earth's surface, where energy from sunlight is most readily available. The distribution of life is extremely uneven. Neotropical rainforests cover only 6% of Earth's land surface, but contain approximately 50% of terrestrial species. Ocean life concentrates near coasts and in upwelling zones where nutrients are abundant, while vast regions of the open ocean are relatively barren. The total biomass on Earth amounts to approximately 550 billion metric tons of carbon, with plants accounting for approximately 450 billion tons, or 82% of the total. In contrast, animals represent only about 2 billion tons of carbon, with humans accounting for approximately 60 million tons. This means that all humans combined represent roughly 0.01% of Earth's total biomass. But humans have had an outsized impact on Earth's biosphere. The biomass of livestock that humans raise for food now exceeds the biomass of all wild mammals by a factor of approximately 15 to 1. Domesticated animals now dominate Earth's mammalian biomass in a way that has no precedent in the fossil record.